Rhoades from the Center for Communication Research in Princeton will talk about very, very interesting talk about set partitions. As usual, we're going to take this out of town speaker for dinner. If you'd like to join us, please let me know immediately after the talk.
Great. Thanks. Right, so I'm going to talk today about set partitions and sort of understanding what I'm interested in doing is sort of understanding what a set partition looks like by understanding sort of what the statistics look like for sort of random partitions. And I'll talk about the uniform distribution on set partitions, which I guess you have heard recently about sort of other distributions on set partitions. And the uniform one is the natural one, and the sort of the problem that when it came to me. So everything I'll talk about is joint with three people. So Bobby Chern, who's a graduate student at Stanford, and Percy Taikonis, who's a professor at Stanford, and Dan Kane, who at the time was another postdoc at Stanford, but now he's at UC San Diego. Okay, so everything I talk about is joint with all of them. So whenever I talk about a set partition, I'll talk about partition of the set 1, 2, up to n. Okay. So set partitions are kind of basic objects in combinatorics, and there's a lot of different encodings of set partitions, which, depending on what your sort of application or the world you come from, a different encoding might be, better than one encoding might be better than another one. You pass this back. So, okay. So, for example, if n is 3, you can just write it in terms of its blocks. So, like 1, 2, 3. This means that 1 is in a set by itself, 2 is in a set by itself, 3 is in a set by itself. You have 1 and 2 together, and 3 is off by itself, or 1 and 3 together, and 2 is off by itself. Or 1's by itself, and 2 and 3, or 1, 2, and 3 are all together in the same block. Right? An encoding that I am particularly fond of is, or what I call arc diagrams. So you draw a little dot, number them 1, 2, 3, and you connect consecutive elements in the same block. So this is kind of boring, but here, because 1 and 2 are in the same block, you connect them. Here, 1 and 3 are in the same block, so there's an arc between them. 1's in its own block here, but 2 and 3 are connected. And here, 1, 2, and 3 are all in the same block, so you draw arcs this way. You don't draw the arc from 1 to 3 because 1's connected to 2 and 2 is connected to 3. Okay. So those are kind of arc diagrams. There's restricted growth sequences. These are, if you're going to enumerate these things, probably this is the nicest way to think about them. They are what they sound like. You start with like 0, and your sequence can't grow too quickly, right? So it only can go up by 1 more than the maximum of what you had before it. So here, this sort of trivial part of the partition where each of them are by themselves corresponds to this sequence. This one, well, 1 and 2 are in the same thing, so it's 0, 0, 1. Here, 1 and 3 are the same thing, but 2 is sort of off by itself. It's like that. This is 0, 1, 1, and here's 0, 0, 0. Okay, so restricted growth sequences. Okay, the number of set partitions of a given size is the Bell number. So essentially, I'll write a B so that it's the Bell number. So these are all the set partitions on 3 objects. So I'll make a little table. Here's n given 1, 2, 3, 4, 5. There's 1, 2, 5, 15, 52, so on. The Bell numbers, there's nice recursion to compute them. So here's recursion that is just reminded of a minute ago. Right, so if you want to compute the first few, this is a pretty good recursion for computing them. There's a Stirling-like approximation for the Bell number. So Bn is approximately, well, like Stirling numbers are like n factorial is like n over e. This is like n over alpha n to the n, which is about n over log n to the n, where alpha n is the solution to this equation.
Could you replace n minus k by k in that sum? Would it be simpler?
And this one?
If you replace n minus k by k,
yeah.
would it be simpler?
Yeah, but then it would make less sense in my brain. So, okay, so these are sort of, set partitions, Bell numbers. That's like kind of how you count them, and they come up in a lot of places. So the problem that I'll talk about was motivated by a problem that Percy told me about, and so some of the other places where he told me these things show up are in, so like statisticians care about them when they do like cluster analysis or something, and physicists, there's some kind of Markov chain on set partitions that's kind of, it's pretty interesting. I don't understand the physics of where it arises from. Combinatorialists, obviously, there's a lot of combinatorics where these come up, and group theorists actually as well care about them. And so there's like representations of the symmetric group, there's all this combinatorics with integer partitions, and there's a certain unipotent matrix groups that have really their character theory, their sort of representation theory is like really wild behavior, and there's sort of an approximation to it called supercharacters, which the way to sort of encode them is through this set partition data. And so the question that that Percy asked me was, if you have some set partition of n, or say so a random one, then what do the sort of, well, he called it the dimension, exponent, and crossing numbers look like? Okay, so the dimension exponent, it's a statistic. What you do is you sum over all the blocks. You take the biggest thing in the block, you subtract the smallest thing in the block, you count that all up. And then you add some easier stuff. This is the number of blocks. That's my notation for it. And then you subtract n. Okay, so it's a set partition of n. So if you look at random, fix some n, look uniformly at random inside that set, and you say, what does this tend to look like? Okay. And the other thing, that is the dimension exponent, because it corresponds to the dimension of some representation, and the crossing, he called it the intertwining number, but its crossing number is more natural. It's the number of crossings in the arc diagram. So it's the number of times that you see arcs that cross like that. Right? So it's maybe I prime, J prime. Yeah.
You've always got to go above the line.
Yeah.
You can't sneak.
That's right.
Underneath.
Right. I mean, yeah, that's right. Okay. So those are the questions. So let's do an example. So 1, 2. I'll do the same one here so that I get the arithmetic right there. 1, 2. Okay. So here's a set partition. Here's the arc diagram for it. So the number of crossings is easy. You can see there's like 1, 2 crossings. The dimension here, the dimension exponent is, well, you have to look at every block, and you take the maximum thing in the block and you subtract the minimum thing in the block. So 1 and 7 are in a block all by themselves. So that's that. 2 and 3 are in a block all by themselves. 4 and 6 are in a block all by themselves. And then 8 and 5. Right? And then I need to add the number of blocks I'm supposed to add it, right? Yeah. Which is 4, and I subtract 8. So this is 6, 7, 8, 9, 12, 16, minus 8, so that's 8. Okay. So that's the dimension number for this partition. Okay, so all right, so asking questions about statistics on set partitions is like a really long, history. So a question like, okay, so one question that people ask for like, how many blocks are there on average, or how many blocks of size 2 are there, or what's the size of the longest block, or things like that. So questions like that have a long history. But what's a little bit different about these problems is that they care what's inside of the blocks, right? Like here I actually care, I don't really care how many, well I care how many blocks there are, but what the important the interesting thing here is that you care about what the biggest and smallest elements inside of each block are. So it's sort of, it has a little bit of a different flavor than a lot of the classical questions about random set partitions. Okay, so if you look at the first page of the handout, I have some numbers and things that they look at. So okay, so first he asked me this question. I don't know if I computed a little bit. So at the top I recorded all the dimension and crossing exponents for the partitions of 3 things. So you can see the dimension exponent. There's one thing that has dimension exponent 1, and then the other 4 have dimension exponent 0.
Is the definition here the same as that one?
Yeah, it's the same. The only difference is that I put a +1 in here, and then in here I pulled that +1 out and just wrote number of blocks. Because I wanted to introduce some notation here. And there I just literally cut it out of a paper I wrote and pasted it on there. Okay. So, okay, and then below that is the sort of histogram, right? So it has, for a fixed n, it has the count for how many set partitions there are of that, with that dimension exponent, right? So you can see when n is 3, there are 4 with 0 and 1 with 1. Right? That's what was in that little table up there. Okay, so those are a few numbers, and you might see a pattern down the first column there, and the next one you might even see a pattern too. But there's weren't a lot of patterns in there that I could see, so I said, okay, I'll keep thinking about things and keep going. I made a histogram.
Is that table in OEIS?
Yeah, I think it is now. I think at some point it was added. I think. Yeah. I told Bobby to do it, so if it's not there, it's his fault. Okay, so I made a histogram, and if you make that a histogram when n is 20, it looks pretty normal, right? I mean, the answer to this question is that it's normally distributed. I mean, you look at that histogram, it's normally distributed. So there's another histogram there, which is when n is 100. Okay, and it still looks really normally distributed. So these are, okay, so the answer to this question is that it's normally distributed. You just look at it and you can see. Right?
Okay. Asymptotically normally.
Yeah, asymptotically. Yeah. Which is what Percy wanted. So, okay, so one thing maybe worth pointing out here is that when n is 20, the bell number, the 20th bell number is like 10 to the 45. Okay, so that's a pretty big number. And when it's 100, it's like 10 to the 384. So I didn't make this picture by generating every set partition, computing the dimension exponent, and then making a big count, right? So we have some sort of a recursive way to compute these distributions. Okay. So there are 3 things that I want to talk about today. Let's try to get across. And the first is, so there's 3 things. The first is going to be this kind of recursive technique for computing these distributions, which is as far as I know, I hadn't seen this trick before. So I think it's a pretty cool trick to compute these. So this is to compute these distributions. The second thing that I want to talk about are moment formulas. Okay, so Percy, well, it's okay. It looks normally distributed, but what's the mean? What's the standard deviation? What are those things? And it's about computing those formulas in really an algorithmic way. Okay. And the third thing, which I maybe won't have enough time to talk about, which is Stam's algorithm for generating random set partitions. But I think that it's an algorithm. But it's actually very powerful in actually trying to prove results such as this asymptotic normality. Okay, so let me start by talking about this recursive technique. Okay, and the idea is really simple. So what you do is you fatten up the definition of set partitions to include what we call them marked set partitions. Okay, so marked set partition. So what you do is every block is either blocks are open or closed. Okay? I don't know if maybe this is a trick people have seen before. I don't know. But I thought it was pretty nice. Okay, so I'll just illustrate it with an example. So I'm going to have some here's the statistic that I'll compute on these marked set partitions, okay? What I'll do is I'll sum over all my closed blocks, the maximum, okay? And then I'll subtract over all the blocks, open or closed, the minimum thing in that block. Okay? I'll add to it the number of blocks, and then I have this extra little term that makes the recursion work out nicely later. Here, this is the number of open blocks.
And you want to tell what is open and closed block?
Yeah, I'll tell you what's open and closed. Yeah. So what it is that that's all it is. That's all it is. Every block is either open or closed. That's all there is to it. Okay. But now our goal is really to compute something where this marking doesn't matter at all, right? So if all the blocks are, in here, if all the blocks are closed, then that means this is 0, and this is exactly the statistic we had before, because they're all closed. So this condition, this is the sum over all the blocks. So this will just be that if all blocks are closed.
So it's a collection of all set partitions where you arbitrarily allow anything to be closed or open. It's all possibilities.
Yeah,
all possibilities.
But every block is marked one or the other.
Right, exactly. So this is like an inclusion exclusion type thing.
Well, it's I don't know if I phrase it that way, but kind of, yeah.
Okay.
Oh, so
sort of.
So you look. So all the possibilities. So is that color?
Yeah, you're coloring all the blocks, basically. There's two colors.
So there's nothing different to open and close.
What's that?
Instead of open and close, you call it red and blue.
You could, yeah. But I'll call it open and closed because what I'm thinking about doing is we want to recurse so that we want to think of it, okay, I want to compute the n+1 things from the n things, right? But now, the way you do that is you can't bring in n+1 and drop it into a block that's already closed. You can only put it into an open block. And that's the rule. That's the game you play. And then when you put it into a block, you can either close that block or you can leave it open.
Oh, so it makes sense.
So that's why it's called open and closed. Right. Okay. So you see. So really now what you do is there's sort of four things when you're trying to recurse. Go to the next guy. n+1 is added to a singleton set. So it creates. So meaning it creates a new block, and that block is open, right? Or you can bring it in, and you can immediately close the block, right? Or you can, n+1 is added to an open block, and you close it, or you can bring it in an open block and leave it open. Okay. So now, instead of just computing the number of set partitions of n with dimension exponent d, you count the number of set partitions of n with this modified dimension exponent d and number of open blocks O. And you use these four rules to define a recursion, and then you just specify that O has to be 0, and you get the original statistic you wanted. And it's fun to play the same game with like crossing numbers or other statistics that you like. So instead of an O of b to the n algorithm, this gives like an O of n to the 4th algorithm to compute the distribution. And that's how you computed the distribution when n is 100. Or much bigger than that. Okay, so that's the first thing I wanted to talk about. I think is kind of a nice trick that I hadn't really seen before.
Could you lift the board instead of erasing?
Sure, can I do that?
Or whichever one.
I tried and I couldn't, so...
It's just heavy.
Okay. Okay, so that's the first thing. So the second thing I want to talk about are these moment formulas. Okay, moment formulas. So let's see. Okay, so the first thing I want to know is what's the average? This is actually, I think, probably the very first thing that I did. All right. So I computed this number, and you can almost imagine sort of computing this. You kind of compute, how many times can 7 be the biggest thing? You can almost you can just do this by hand. Almost. You just think about it for a little bit, and you can compute and find a formula like this. And once you sort of figure out how to compute it by hand, you can kind of compute the second one. Okay, so this gives the mean. This says basically the mean of this statistic, which we know is going to be normally distributed. This tells you the behavior of it.
So do you use the d theta for this?
No, here I'm back to the d.
Ah.
Yeah. Right, I haven't really played these games with sort of this joint statistic or anything like that. Okay, so if you want to know about the standard deviation, you can compute, you can basically do the same kind of thing, and I won't write it here because it's on the handout I gave you. So if you look at the back side of the handout, there's this formula and then this second one there. Because here was my plan. I said, okay, I'm going to compute the moments. I'll compute a couple by hand. I can do that. I'll guess the formula. Once I know the formula, I can prove it. And then I'll prove that the thing is normally distributed because the moments will be right. If all the moments are what they should be, then it's going to be normal. So I looked at this. It wasn't obvious what the pattern was, so I worked out one more. It took me a whole day to work out the next one.
But ideally, a computer should do it.
Well, yeah, that's where I'm going. Right. Okay, so I worked out the next one, and the thing is that there always was a formula, right? These formulas, we call them shifted Bell polynomials, okay? There always was one of these formulas where you'd have these Bell numbers times a polynomial. And the Bell numbers were always like b of n plus 1, b of n plus 2. And if I was working out the third moment, it went up to b of n plus 6, right, was the biggest one. The fourth moment, it would go up to b of n plus 8. There always was this formula.
But it's weird that the b of n plus 1.
Is it?
Intuitively, you think it's b of n minus.
Well, it has to be bigger. And because... Okay. The way the size of things has to work out, if you kind of make a guess for just looking at the data, it's going to grow. The way it's going to grow, and then using the asymptotics for the Bell numbers, you can see that it has to be bigger. But and you can almost get, but you can't quite guess that it's going to be this big. Okay, so I looked at these first three. I showed Dan Kane. I was like, okay, did you see any patterns? And he said, well, work out the next one, and then I'll look at it. And I thought, there's no way I'm working out the next one. It took me all day. But then he said, well, why don't we just prove that such a formula has to exist? Okay, so that's what he did. So prove that a formula has to exist, and then get the computer to find it for us. Okay, so that's the result then. So here's the theorem. Is that for each k, there exists a formula, it's the sum over all the set partitions of n. You take the dimension exponent raised to the kth power. Then there are these polynomials, p of k, 2k of n, b of n plus 2k plus. So the first one is the power on the exponent, and then the second subscript here is the shift of the Bell number. So on. It goes down to b of k, 0 of n, b of n plus, 0. Right. Okay, and moreover, the degree of these, the degree of p of k, 2k minus j, is, well, less than or equal to, it's j, or it's k minus the ceiling of j minus k over 2. This is if j is smaller than k, and this is if j is bigger than k. Okay. Okay, so prove this formula. It says these formulas, let's prove this theorem. This theorem says the formulas have to exist. We know we can compute the distribution for a lot. So now we got a new plan. So the plan is, first we're going to compute, the distribution for as many n as we can handle. Then we're going to solve for this formula, the sum of d of k, d of lambda to the k, for as many k as we can. Then we're going to, find the pattern. All right, and then, then we'll prove that d of lambda is normally distributed. Asymptotically, right? Okay. Well, on the handout, there's a couple more of the examples. So this, on the bottom left here, I have it says doing k equals 1. I mean, it means the computer is doing k equals 1, and then spit out those polynomials. So the polynomials, you'll recognize them from the first formula there. There's a 4 plus n and a minus 2. That was from the average. Then the next one, there's these other polynomials. So you'll recognize n squared plus 8n plus 9, which was in that second formula up at the top. And there's the third one, and the fourth one, and the fifth one. We stared at them, and we didn't see any patterns. So
when you're working with these Bell numbers, it's nice to work umbrally. Are you familiar with the term umbrella?
right.
Instead of b sub k, you think of it as b, the variable b to the power k. If you did that there, do they factor? Do they simplify? Because
They would. Well, how do you so how do you deal with multiplying by n or something?
you just, any subscript on b, you raise it up, make it
Yeah, instead of b
nicer.
sub n plus k, will be b to the power n plus 2k. And they have a polynomial n.
And then you try to factor this sort of thing.
Yeah, the polynomial
You'll notice hints of that if you stare at these things long enough, but it won't work out, I think, as well as you'd like it to. Okay, so that's a good question. I don't know. So people who know more about that,